Something was found on Neptune, and the scientists who found it went quiet for a reason, not the kind of quiet that comes after a boring discovery, the kind of quiet that comes when you realize the universe just broke one of your oldest assumptions. The James Webb Space Telescope pointed its golden mirrors at the farthest planet in our solar system, a world so distant that sunlight takes over 4 hours to reach it. And what it sent back didn't just surprise astronomers. It astonished them. It rewrote temperature records, it revealed glowing lights that no instrument had ever seen before, and it opened a question so large that nobody yet knows how to answer it. Nobody was looking at Neptune. That is the honest truth that most science channels will not tell you. When the James Webb Space Telescope launched into space in December 2021, the scientific community was buzzing about exoplanets, about deep galaxies, about the earliest light of the universe. Neptune, that cold, dark, distant blue giant sitting more than 2.7 billion miles from Earth, was not exactly the centerpiece of anyone's grand ambitions. It was the forgotten planet, the one that gets mentioned last in solar system diagrams, the one schoolchildren sometimes confuse with Uranus, the one that, for decades, scientists had essentially filed away in a mental drawer labeled, "We'll get back to this eventually." But someone decided to look, and what they found has fundamentally altered what we thought we understood about this planet, about our solar system, and, if you follow the implications all the way to the end, about planetary science across the entire universe. Let's start with what we knew before James Webb arrived. The last time any spacecraft had actually visited Neptune was 1989. That was when NASA's Voyager 2 probe made its historic flyby, screaming past the planet at tens of thousands of miles per hour, snapping images and collecting data in a window that lasted only a matter of hours. 34 years of planetary science built on a single afternoon's worth of data. Think about that. Every model, every prediction, every textbook chapter about Neptune's atmosphere, its magnetic field, its temperature, all of it was constructed on a foundation that was already decades old before James Webb even began construction. Scientists were essentially working from a photograph taken before many of their graduate students were born. And Voyager 2, brilliant as it was, had limitations. It recorded what it could, with the instruments it had, in the time it was given. It told us Neptune's upper atmosphere had a certain temperature. It hinted at the existence of auroras, those magnificent glowing light, displays caused by energetic particles crashing into a planet's atmosphere, but could never confirm them. The technology simply wasn't sensitive enough. So scientists wrote it down in their notebooks, published their papers, and moved on. The hunt for Neptune's auroras was placed on a shelf labeled Unfinished Business. But here's where it gets strange. For the next 3 decades, astronomers tried repeatedly to find those auroras from Earth. They pointed the Keck telescope in Hawaii at Neptune. They turned the NASA infrared telescope facility toward it. They searched for a specific chemical fingerprint, a molecule called the trihydrogen cation, written as H3+, which is created in auroras and has been the calling card of auroral activity on every other gas giant in our solar system. Jupiter has it, Saturn has it, Uranus has it. These 3 planets gave up their auroral secrets relatively easily, identified and confirmed more than 30 years ago. Neptune was the one holdout. Neptune was the one planet where every search came back empty. And the longer that emptiness continued, the more uncomfortable the silence became. Because Neptune should have had auroras. Every model said so. Every physical understanding of how solar wind interacts with planetary magnetic fields predicted that Neptune, with its powerful and bizarre magnetic field, should be producing auroral light. But no one could find it. And in science, when reality consistently refuses to match theory, one of 2 things is happening. Either the theory is wrong, or something about the planet itself has changed. So what James Webb discovered is that the answer is far more unsettling than anyone anticipated. In June of 2023, researchers used James Webb's near-infrared spectrograph to point at Neptune and search for what all those previous instruments had failed to find. The near-infrared spectrograph, NIR spec, is not just a more powerful version of what came before. It operates in a wavelength range that was previously inaccessible from any other space telescope or ground-based observatory. It sees light that other instruments are essentially blind to. And when it looked at Neptune, it found something that made lead researcher Henrik Mellon, a planetary scientist at Northumbria University, use the word astonished, not pleased, not encouraged, astonished. The trihydrogen cation was there, unmistakably, undeniably there. Webb had found it in an extremely prominent emission line, a chemical signature so clear and so strong that there was no room for doubt. Neptune had auroras. But that discovery, monumental as it was on its own, was not even the most alarming thing in the data. Because alongside the confirmation of auroras, the Webb team had also measured something else. Something that nobody had measured in 34 years. They measured the temperature of Neptune's upper atmosphere, its ionosphere, for the first time since Voyager 2 flew past in 1989, and the number they got back stopped them cold. Neptune's upper atmosphere had cooled, not by a few degrees, not by the kind of marginal fluctuation that falls within the noise of a scientific instrument. Neptune's ionosphere had dropped in temperature to roughly half of what Voyager 2 recorded in 1989. Half. We are talking about a cooling of several hundred degrees, on a planet that already sits in one of the coldest regions of our solar system, in an atmospheric layer that previous models suggested should be comparatively warm. This was not a data anomaly. This was a planetary transformation, and nobody had noticed because nobody had looked. Think about what that means. For 34 years, scientists were predicting Neptune's auroras based on a temperature reading from 1989. Their models said, given this temperature, the auroras will have roughly this intensity. And since they could never find auroras matching that predicted intensity, they assumed the instruments weren't sensitive enough. They assumed it was a detection problem. But it wasn't a detection problem at all. The auroras were fainter because the planet was colder. The entire atmospheric energy balance had shifted, and every model built on Voyager 2's data was quietly, invisibly, catastrophically outdated. According to the study, published in the journal Nature Astronomy in March 2025, the average upper atmosphere temperature of Neptune is now roughly a factor of 2 cooler than what Voyager 2 measured. The research team, including scientists from Northumbria University, the University of Leicester, Boston University, and NASA's Goddard Space Flight Center, confirmed that this dramatic cooling shows that the energy balance of Neptune's ionosphere is regulated by physical processes, operating on a timescale shorter than both Neptunian seasons, which last approximately 40 years, and the 11-year solar cycle. In other words, whatever is driving these temperature changes is responding faster than the seasons and faster than the sun's own activity cycle. Something is happening inside or around Neptune that science has not yet identified or explained. And this is where everything changes, because the moment you realize that Neptune's atmosphere has transformed dramatically over the last 3 decades, you have to start asking a very uncomfortable question. If we got Neptune this wrong, if the most fundamental measurement we had about this planet, its temperature, was already ancient history and nobody knew, what else have we gotten wrong? And that question does not stay neatly contained to Neptune. Let us talk about the auroras themselves, because they are stranger than most people realize, and that strangeness tells you something profound about this planet's hidden interior. On Earth, auroras appear near the poles. The northern lights dance above the Arctic. The southern lights illuminate the Antarctic sky. This happens because Earth's magnetic field is relatively simple and relatively well behaved. Its magnetic axis is aligned within about 12 degrees of its rotation axis. So when charged particles from the sun stream inward, they follow the field lines toward the poles and light up the sky there. It is elegant, predictable, and photogenic. Neptune is not any of those things. When Voyager 2 discovered Neptune's magnetic field in 1989, scientists were genuinely baffled by what they found. Neptune's magnetic axis is tilted not 12 degrees, not even 30 degrees, but 47 degrees away from its rotation axis. 47 degrees. And if that weren't disorienting enough, the entire magnetic field is also offset from the planet's center by about 40% of Neptune's radius. Imagine taking Earth, tilting it dramatically to one side, then shifting the magnetic North Pole from the Arctic all the way to somewhere over Central Europe, and you have only begun to approximate the geometry of Neptune's magnetic environment. One scientist from Imperial College London once described it this way, and the description has never been improved upon. Imagine taking the Earth, tipping it over diagonally, and then moving its magnetic North Pole to Central Europe, and you start to get a sense of what Neptune is like. This bizarre tilt has a direct consequence for the auroras. Because auroral activity is anchored where magnetic field lines converge into a planet's atmosphere, Neptune's auroras do not appear at its rotational poles. They appear at mid-latitudes, wandering across the planet's face in patterns that shift with every rotation. As Neptune spins on its axis, completing one rotation roughly every 16 hours, the misaligned magnetic field wobbles through space like a lopsided gyroscope, creating a magnetosphere that constantly reshapes itself. The Webb telescope captured this in action, detecting enhanced auroral emission in Neptune's southern hemisphere, appearing in what researchers described as the post-noon sector. The aurora was not steady. It was localized, concentrated, and shifting, a glowing bruise drifting across a blue world that no human eye will ever see up close. But why is Neptune's magnetic field so tilted? Here is the real secret that the mainstream discussion keeps glossing over. We do not fully know. The leading explanation involves Neptune's interior structure, which is fundamentally different from Jupiter and Saturn. Neptune is classified as an ice giant, not a gas giant, and that distinction matters enormously. Where Jupiter and Saturn are dominated by hydrogen and helium, Neptune's interior is thought to contain a thick layer of water, ammonia, and methane, compressed under such extreme pressures that they exist in a strange high conductivity state, sometimes described as a superionic or ionic fluid. Unlike the Earth's solid inner core, which stabilizes and anchors the magnetic field, Neptune's interior is thought to be layered liquid that does not convect uniformly. Instead, convection is thought to occur in a thin outer shell, generating a magnetic dynamo effect that is chaotic, asymmetric, and unanchored by any solid core beneath it. The field lines tangle, they loop, they shift. The result is a magnetic environment of almost unparalleled complexity in our solar system. And here is what makes the Webb discovery so significant from a theoretical standpoint. By detecting Neptune's auroras and measuring their spatial distribution, scientists now have a new observational window into how that twisted magnetic field is actually functioning in real time. Every aurora is, in a sense, a map. It shows you where the magnetic field lines are funneling energy into the atmosphere. By studying Neptune's auroras in detail, their location, their intensity, their movement, scientists can begin to reconstruct what is happening inside a planet they have never visited with modern instruments and may not visit again for decades. The aurora is a diagnostic tool, and Webb just handed them the most powerful diagnostic tool they have ever had. The implications extend far beyond Neptune. According to informed sources in the planetary science community, the reason this discovery generates such intense interest is not simply what it tells us about one distant blue planet. It is what it tells us about ice giants as a class of worlds. Uranus and Neptune together represent a category of planet that, until recently, was thought to be relatively rare and scientifically marginal. But as James Webb and other modern observatories have scanned the galaxy for exoplanets, planets orbiting other stars, a startling pattern has emerged. The most common type of planet in the observable universe appears to be something close to the size of Neptune. Not gas giants, not rocky terrestrial worlds, something in between. Mini Neptunes and sub-Neptunes may, in fact, be the most abundant type of planet in existence. And yet, until Webb looked at our own Neptune with new eyes, we had almost no modern understanding of how these worlds actually work. What most people are not seeing is the full cascade of what this discovery unlocks. Scientists now know that Neptune's upper atmosphere is capable of changing dramatically over timescales of years to decades. That is not a planetary curiosity. That is a critical data point for modeling the atmospheres of every Neptune-like planet in the galaxy. When astronomers study a sub-Neptune exoplanet hundreds of light years away and try to determine whether it might host conditions compatible with complexity, with chemistry, perhaps even with biology, they need models built on solid observational foundations. For decades, those foundations were cracked. Neptune, the nearest and most accessible ice giant, was built on measurements that were already a generation out of date. Webb just replaced that crumbling foundation with something new. Now, let us follow the temperature mystery further because it does not resolve neatly, and the lack of resolution is the most important part. A drop of several hundred degrees in Neptune's upper atmosphere is extraordinary. Scientists confirmed it in data published in March 2025. But what caused it? The honest answer, the one that doesn't get enough attention in the celebratory headlines, is that nobody is certain. Neptune sits more than 30 times farther from the Sun than Earth does. At that distance, sunlight is roughly 900 times weaker than what we experience. The Sun's influence should be negligible, and yet the dramatic cooling, and the fact that it appears to be responding on timescales shorter than the solar cycle, suggests that solar activity still reaches into Neptune's atmosphere in ways that our current models do not adequately capture. The Sun's reach, it turns out, extends deeper into the outer solar system than we thought. Neptune, 4.5 hours of light travel time away, is still somehow connected to the rhythms of our star. The research team, led by Mellon and including scientists across multiple institutions, has proposed studying Neptune through an entire solar cycle, an 11-year monitoring program using Webb. Their goal is to understand how Neptune's ionosphere responds to changes in solar activity over time, to build the kind of longitudinal dataset that Voyager 2's brief flyby could never provide. This is not a small undertaking. It requires sustained telescope time on one of the most expensive and oversubscribed scientific instruments in human history. The fact that the scientific community is seriously proposing it tells you how significant this discovery is regarded to be. There's also the question of Triton, Neptune's largest and most enigmatic moon, which adds yet another layer of complexity to this already deeply strange system. Triton is a captured object, not a moon that formed alongside Neptune, but a body from the outer reaches of the solar system that was gravitationally captured at some point in Neptune's ancient past. It orbits Neptune in the wrong direction, traveling opposite to the planet's rotation in what is called a retrograde orbit. Its surface has active cryovolcanoes, geysers that erupt not with molten rock, but with nitrogen gas erupting through ice, shooting dark streaks across its southern polar cap that Voyager 2 photographed with astonishment in 1989. And Triton is slowly spiraling inward. Over millions of years, tidal forces are drawing it closer to Neptune, and the eventual outcome, still billions of years away, is that Triton will be torn apart, its remains scattering into a ring system around Neptune that will dwarf anything the planet currently has. The Webb telescope, looking at the Neptune system with its extraordinary infrared sensitivity, has placed all of these pieces into a new context. The auroras, the temperature anomaly, the tilted magnetic field, the captured moon with its backwards orbit and active surface, these are not independent mysteries. They are facets of a single, coherent puzzle about a planetary system that formed and evolved in ways that are still deeply unclear. Informed sources in Planetary science increasingly suspect that Neptune's bizarre magnetic field is connected to its interior thermal structure, which is itself connected to the heat that Triton's capture generated billions of years ago, which continues to radiate outward today. Neptune emits significantly more heat than it receives from the sun, a characteristic it shares with other giant planets, but to a degree that remains poorly understood. Something inside Neptune is still warm, still active, still releasing the energy of its violent past. And here is the detail that tends to get buried in the technical language of published papers. Neptune's upper atmosphere cooled by half since 1989, but its deep interior is still radiating excess heat. These two facts, taken together, suggest a planet in which different layers are operating on completely different energy schedules, where the surface is cooling rapidly while the interior remains warm, where the magnetic field is churning chaotically while the auroras glow faintly at mid-latitudes, where a backwards moon slowly spirals toward its eventual destruction. This is not a simple, stable, well-understood world. This is a planet actively in transition, governed by processes that we are only now beginning to witness with instruments sensitive enough to capture them. This is not chaos, this is process. Ancient planetary-scale process that we have only just started watching. The published results from the Webb observations of Neptune appeared in the journal Nature Astronomy on March 26, 2025. The paper is titled, Discovery of H30+ and Infrared Aurorae at Neptune with JWST. The lead author, Henrik Mellin, described the moment the data came back in terms that are worth dwelling on. He said that it was stunning not just to see the auroras, but that the detail and clarity of the signature genuinely shocked him. Lee Fletcher of the University of Leicester, one of the co-authors, noted that this observatory had finally opened the window onto what he called the last previously hidden ionosphere of the giant planets. Every other giant planet in the solar system, Jupiter, Saturn, Uranus, had given up its ionospheric secrets years or decades ago. Neptune had held out for 35 years, and when Webb finally pried that window open, what it found behind it was both confirmation and surprise simultaneously. The real story is that this discovery changes how scientists will approach Neptune going forward, and it changes what they will look for. Before Webb, the plan for studying Neptune remotely was limited by the available instruments and the outdated baseline data from Voyager 2. Now there is a new baseline. Now there is confirmed auroral activity that can be tracked over time. Now there is a temperature measurement, radically different from what was previously known, that resets every model. And now there's a scientific imperative to return, either with Webb continuing its observations or with a dedicated mission to the ice giants. The case for sending a spacecraft to Uranus and Neptune has never been stronger. And within the planetary science community, a flagship mission to Uranus has already been identified as the highest priority large mission in NASA's most recent planetary science decadal survey. Neptune is not far behind that conversation. But a spacecraft mission to Neptune, even if approved and funded tomorrow, would not arrive for decades. The distances involved are almost incomprehensible. Voyager 2 traveled 12 years before reaching Neptune in 1989. A new mission optimized for the current planetary alignment would face similar challenges. So, in the meantime, James Webb is doing something no previous telescope could do. It is acting as a remote sensing station for a world that we cannot visit, extracting chemistry, temperature, and atmospheric dynamics from light that has traveled across billions of miles to reach its mirrors. And Webb is not done. According to the research team, future observations will focus on tracking how Neptune's auroras change across different time points in the solar cycle, building what will eventually become the first long-term atmospheric record of Neptune in the modern era. They will be looking for seasonal changes, for responses to solar activity, for clues about whether that extraordinary temperature drop is a permanent new state or part of a longer oscillation that Voyager 2 simply happened to catch at one particular moment in the cycle. They will be asking whether the cooling has continued, stabilized, or reversed. They will be asking whether the magnetic field has shifted since 1989, and whether Webb's auroral data can begin to constrain new models of what Neptune's interior looks like. What we are witnessing, in other words, is science in the process of rebuilding its understanding of a world from nearly nothing. Not from a place of ignorance. Decades of theoretical work and indirect observation have given scientists a sophisticated framework to work within, but from a place of observational poverty. For 35 years, the most advanced instrument we had trained on Neptune's atmosphere was Voyager 2, and Voyager 2 was flying past at high speed during the Reagan administration. James Webb has now given planetary science something it has never had for Neptune, a stable, powerful, deeply sensitive observatory that can look and look again and look a third time and compare what it sees and build the kind of data set that transforms curiosity into understanding. Neptune is 2.7 billion miles away. Its light reaches us already old. By the time the photons that Webb's mirrors caught in June 2023 had made that journey, they were carrying information about a world that the human species has visited exactly once, for exactly a matter of hours over 3 decades ago. And yet, within those photons was enough information to rewrite temperature records, confirm a 35-year mystery, reveal a magnetic field behaving in ways that still lack complete explanation, and open questions about solar influence that reach deeper into space than any model previously suggested. What else is Neptune hiding? That question is no longer rhetorical. It is a research agenda, and James Webb is the instrument that will pursue it, one observation at a time, one aurora at a time, one data point building on the last, until the picture sharpens into something we can finally hold up to the light and say, yes, now we understand. Now we see what is really there. But that moment has not arrived yet. The data is still coming in. The models are still being revised. The scientists are still, in the most literal sense, stunned by what they found. And somewhere out there, 4.5 hours from sunlight, a planet is glowing with auroras that nobody knew existed until last year, cooling in ways that no model predicted, spinning with a magnetic field that breaks every rule about how planetary magnetism is supposed to work, dragging a captured moon slowly inward toward its doom, radiating excess heat from an ancient, violent past that nobody fully understands, and rotating through a solar system that we thought we knew. We did not know it. We are only beginning to look, and the more carefully we look, the stranger it becomes. What else has Neptune been hiding for 35 years? And what else? Across this solar system, across this galaxy, across every ice giant orbiting every star we have ever catalogued, have we been confidently mapping without ever truly seeing? That is not a question with a comfortable answer. That is a question that keeps planetary scientists awake, and it should.